Hi, this is the recording for topic 4, organic molecules. In this topic, we mainly talk about four major micromolecules, big organic molecules that existing in our body. And these four, oh, yes, good. So this four is proteins, carbohydrates, lipids, and the nucleic acids. And nucleic acids, we have an independent topic later called the DNA to talk about more nucleic acids in details. So in this chapter, we mainly talk about proteins, carbohydrates, and lipids. So first, let me change, yes. Let's talk about proteins. Proteins. And proteins, carbohydrates, and some of those fatty acids are collected called polymer. What is a polymer? A polymer is made up by monomers. And so that's the universal way in our body to make a big molecules. In our body, we have many big molecules. You can read in my slides, they are way, way larger than the smaller than the inorganic molecules or smaller organic molecules. And the way that life eventually adapt or evolve to make big molecules is to connect small molecules as the let's say construction units to make them in a big molecule. And then the proteins is a big molecule, a big polymer, and this monomer is called. So this is a polymer, and the monomer protein is called amino acid. This is the monomer. And so what's the structures of amino acid? Amino acid have a carbon in the center, and one side it has a amine group, and the other side has a carboxyl group. There's a hydrogen here and a R. So here, this is a base, and this one is a acid, and this one is variable. In our body, we have about 20 different, we call it standard proteingenic amino acids. All of those standard amino acids, I would say 99.99% of proteins are made of the 20 standard amino acids. There are only some exceptions, which we do not have to discuss in this class. And then that's one feature about the 20 amino acids. And also, all of those 20 amino acids, each one of those has at least one genetic codon, which means they are coded in the genes. How we talk about later. And then all the 20s are different in this R group. The R group can be a very simple as a hydrogen or another carbon like this, or many different things. So based on the feature of the R group, we can write this amino acid into mainly four groups: nonpolar, or actually in some cases we just divide them into polar and the nonpolar. Nonpolar is hydrophobic. Later on, we talk about protein folding. Put the nonpolar amino acids in the center, in the interior, and polar in outside. And based on polar amino acids, it can be no charge, positive, or negative. And then another special call it aroma, whatever is this protein carry a, let's call it Bennis. Bennis is, I guess, how we pronounce it. Bennis is a group. In many cases, this kind of amino acids have some sense that we call it aromatic amino acids. So, how amino acids join to a protein? At the beginning, amino acids join together, and this one, how two amino acids join together? This we call it peptide bond. A peptide bond is the reaction of one of the the base of one amino acids react with the acid of another amino acid, and then acid base react with each other and make a bond. And this is a covalent bond. This covalent compound called it a peptide. And then when multiple amino acids join together by peptide bond, this thing we call it a peptide. And the sequence, so here amino acids, a peptide may contain different amino acids like A, C, L, D. And by the way, amino acids, we have 20 standard amino acids. Each one of those has one letter as a symbol, as a name, abbreviation, and a letter. So an R, D, whatever. And this sequence, this amino acid join one by one. This we call it amino acid sequence, and this we call it a primary sequence of amino acids. And then this amino acids, they spontaneously will join if folded by itself. And the first way to fold it, they may form some of those very regular structure. This is called alpha helix, or something like this. This is called beta sheet. And this standard structure of amino acid, we call them secondary structure. And then a polypeptide, a long peptide, contain more than 20 amino acids, we call it a polypeptide. A polypeptide will further, a polypeptide, not every single amino acid will join an alpha helix or beta sheet. Yeah, and actually the third one called it delta chain. That delta turn, which is not discussed in this class. Delta turn, I believe that's the name. And then, but not every single amino acids form this regular secondary structures. There are other special structures, and those special like this, that go in something else, and then along beta sheet, and then another, I just made it up, and then nothing. So eventually, including this special folding and the secondary structure, this polypeptide eventually finally fold into some special 3D structure. This called it tertiary. I'm not sure my spelling is correct actually. Tertiary. And then next level of protein, many proteins is made of more than one polypeptide. And some of those made like one, and another one, and another one, another one. This is one protein made of 4 different polypeptides. Each one of those, we call it a subunit. So the subunits join together. This we call it quaternary. I'm not sure my spelling is correct. Again, quaternary structure. And please keep in mind that not every protein has a quaternary structure, because some protein has only one subunit. So this, and then last thing about the protein is, we already mentioned this, called it protein folding. For example, this is a polypeptide. When it first made a polypeptide, it's like this, a linear, and then very soon a linear polypeptide will spontaneously, I just made an example here, fold it into a 3D structure. This process, that a linear polypeptide spontaneously folded into a functional 3D structure, we call it protein folding. And protein folding, again, is spontaneous. You don't really need anything. In most cases, you don't need anything, but some extra help, some extra protein may help, but you don't really need any, let's say, enzyme to drive it happen. So, and then what kind of a power or initial mechanism that drive this folding? Many different bonds drive this folding. For example, this is called a bisulfite bond. Okay, I'm sorry about my spelling. I'm not sure. It's a covalent bond. So covalent bond is a two, I call it amino acid, call it cysteine, I think so. Two amino acids both have sulfide. When they join together, called it bisulfite bond, the covalent bond, and then some form a ionic bond. Some of those two amino acids, both ones carry a negative charge, the other carry a positive charge. They join together, the ionic bond, and so covalent bond, ionic bond, both contribute to the protein folding. But most important, I have to say, I'm not sure I can say most important thing, but I think I can say most important thing is the hydrogen bond. The hydrogen bond also contribute a lot to the protein folding. So in this case, in many of those, this bonding has a potential. Different protein is different, but most of protein, they can be, this kind of bonds, especially hydrogen bond, can be changed, altered, or even destroyed by extreme conditions, such as pH, temperature, pH too low, temperature, and sometimes even higher osmosis structure stress, like high salt, or like organic solvents. All of those can change the bonds, can change the hydrogen bonds, ionic bonds, and then when those bonds change, the protein structure changed. And then at the beginning, if it's only slightly changed, the protein structure only modestly change, and you don't really the protein is no longer as functional as it used to be. But if you return to the normal condition, the protein may be functional again. But in some cases, when this is extremely far away from the normal condition, this protein will never go back. This we call it denature. When denature happens, the proteins completely lost its structure and cannot go back. Not by itself. There's no way to convert a denatured protein back into a normal protein. It's called a denature. And when denature happens, and many things happen. For example, denature may destroy the bisulfite bonds. And one more thing about denature is that, let's say is a protein here. On the surface is polar amino acids. In the center is nonpolar amino acids. When denature happens, in some cases, they expose the nonpolar. This is a regular one, and when denature happens, expose the non-nature protein outside. And then, if there's two denature protein, this nonpolar amino acids join together so that these two proteins attach to each other, adhering to each other. They form they glue together. This is called coagulation. When coagulation, this protein will no longer be dissolved by water, so you cannot change it back. That's, for example, you cook an egg, you cook with meat. All of those cooking of proteins, there's a denature. Once you cook an egg, you can no longer return the egg to a normal status. So that's about the protein. Next, let's talk about carbohydrates. Carbohydrates actually in many cases is actually carbohydrate. Hydrate is equal to sugar. Carbohydrates is a common thing about carbohydrate is we know. This is looks so ugly. This is glucose. Glucose is one of the a common carbohydrates monomer. Glucose is a monomer, a simple sugar. And then, so in our body we have carbohydrate monomers can have at least as small as three carbons, or as much, I think it's 14 carbon items. And in our body, the most common carbohydrates have two types. Either we call it hexose. Hexose have 6 carbons, and most of those are involved in energy storage or provide energy to other molecules. For example, glucose. Another thing is pentose. Pentose have 5 carbon, like a pentagon, have 5 angles. So pentose is mostly involved in the structure. For example, ribose. We'll talk about more later. The ribose is an essential component of DNA and RNA. And in this class, we mainly talk about glucose next. So next we introduce 3 major different carbohydrates, or not just carbohydrates. We call it is it polymers? Start with poly. Saccharides. Saccharides itself means sugar. Polysaccharides, multiple joined together. And one of the common polysaccharides is not produced by us, but related to us closely. They are starch. Starch is a major source of carbohydrates in our food. So how starch is made up? Starch is made only by glucose. And then this glucose, I'm very bad at drawing, to be honest, right? Is that right? I'm not sure it's right. So this is the one. Oh, actually 1, 2, 3. Yep. Here, 5. I think that now I get it. Here. E. Yes, I think so. 1, 2, 3. E. Look here. 4, 5, 6. Let me draw again. It's so bad. Yes, that's right. So 1, 2, 3, 4, 5, 6. So 6 carbon. In the real world, the glucose is actually not flat. It's like something like this. Something. Yeah. Look into my slides. My drawing is bad, so bad. So, and this curved. Okay. So a 2-glucose in starch is called alpha 1, 2. Alpha 1, 2, 4 glycosidic bond, which means 1 glucose, the carbon 1 is connected to another glucose, carbon 4. This is the 1 to 4, and then they are facing the same direction. So since, just imagine if a glucose is curved, then 1 connect to another one, then connect to another one, another one. So a starch is a helix. A starch is helix structure. And then sometimes they may have a branch. A branch is made by 1 to 6 carbohydrate. 1 to 6 glycosidic bond. In some textbook, you say alpha 1 to 6 it doesn't matter because why so? Because 1 to 6 has only one form, but 1 to 4 has 2 different forms. That's we use alpha and beta. What is beta we talk about later. But anyway, so starch can have this, and then in some places you go another way, and this one keep going, and then another one. There's a starch, and starch. Some of those starch, like say, if you eat the chicken rice, the Jamaica rice. Jamaica rice. I think it's Jamaica rice. Jasmine? Not Jamaica. Jasmine. Probably. Never mind. I call it amylose. Amylose has very low density of branches, low branch. And then another type of starch called amylopectin has high branch. Amylose is not sticky. Amylopectin is more sticky. And then different rice, if you're eating different rice, like sushi rice is more sticky than the jasmine rice. That's because it has more amylopectin. So, and then this is starch. Next, let's talk about another molecule called cellulose. Cellulose, it by itself is kind of soft because you may, I guess everybody has used a tissue paper. Tissue paper is made almost 100%, and 95 or 100 to 100% of cellulose. You can say it's soft, but in the tissue paper, cellulose are all break down into tiny fibers. Like some other cases, like wood. Wood is made of cellulose too. The cellulose wood has about nearly 50% of cellulose, and the cellulose itself is given the strength of the woods. But in both cases, you can tell you cannot eat. You cannot feed on paper. You cannot feed on wood. We cannot digest cellulose. Why? Because, but imagine, the spelling. So, I'm not paying. Okay. So, I forgot what I'm saying. Cellulose. We're going to talk about cellulose. Cellulose actually, you may not think about it, but cellulose, the monomer is exactly the same as starch. It's also made up of glucose. How can it happen? Glucose, actually, we eat glucose when we eat grapes. The sugar, all the sweetness came from the glucose in the grapes. So we eat a lot of glucose in the grapes. And and how come paper, cellulose made of glucose, but it doesn't taste anything and we cannot digest? Because those are made of beta 1,2,4 glycosidic bond. And because of that, I've talked about a glucose is curved, but what if it's in each of those, this is a glycosidic bond, in each of those bonded glucose molecules, they are facing each other, facing a different direction, and then even those single glucose molecules are curved, but they join together, they cancel each other's curvedness. So a cellulose molecule is actually straight, and when it's straight, they are made of two cellulose fiber can get very close, and they are so close they even form hydrogen bond with each other, and this hydrogen bond will bond many cellulose molecules together, and they form a very tight bundle. So in human being, it's very hard for us, firstly, to open up this cellulose bundle, and also we do not have an enzyme to open up this beta 1,2,4 glycosidic bonds. So that's a major difference between the glucose, the starch and the cellulose. We cannot digest cellulose only because the glucose in cellulose are joined up in a different bond. And lastly, let's talk about the carbohydrates or polysaccharides that human being can make themselves, call it glycogen. Glycogen is very similar to starch, only with two things. One thing is glycogen has way more highest branch, has a lot of branch, highest branch of glucose. And then a glycogen is not merely a carbohydrate. In the center, it has a protein. This protein called glycogen. This is the name of protein. It's a dimer. It has two subunits. We just mentioned subunits. There's two subunits, and this subunit is the same. In each subunit, it can hold carbohydrate or polysaccharides can be made out of here. And this carbohydrate chain or polysaccharide chain is made of only glucose. It's again same as the starch, but different than starch is that it has way more branches than the starch. Eventually, form a kind of a spheroid surrounding the carbon the protein core, and this is the glycogen in our body. The liver and the muscle are the two major organs that can make glycogen. And the difference between the liver and the muscle is that so both the similar thing is both the liver and the muscle. After we have a high glucose in the sugar, they grab the sugar glucose from the blood, making glycogen. And then the liver is only a temporary storage of a glycogen. When the blood glucose level reduced, the liver released the glucose back into the blood. But but in the muscle, each single muscle, whenever they grab the sugar into the muscle to make a glycogen, the glycogen stay inside that muscle and be only used by that muscle. So glycogen is a primary energy drive muscle contraction when is in intensive activity. So this is about the polysaccharides. Next, let's talk about lipids. Lipids. Okay. This. Oops. Okay. Lipids. So, lipids. Lipids is a group of molecule of hydrophobic. So lipids is we group all the hydrophobic molecules in our body as lipids. So lipids itself is a category. Here in the category of lipids, we have mainly three different glucose: triglycerides, phospholipids, and steroids. In both triglycerides and phospholipids, their monomer called fatty acid. What is a fatty acid? A fatty acid has a head of acid followed by a carbon chain. The carbon chain may be different numbers. In human, most common is 16 and 18, not 16 to 18, 16 and 18. Even number carbon chain is more popular in the human body than the odd number carbon chain. And then different fatty acids different in their way of how the two carbon join together. In this case, you can see all the carbon are joined up by a single bond, and the rest of those are fully, say, hydrogen, all of the hydrogen. So this we call a saturated fatty acid. And in some cases, you may have a double bond in the center, and this is called unsaturated. Unsaturated means you can still put more hydrogen there. And then the hydrogen can stay naturally. Hydrogen stay on the same side. That's called a cis fatty acid. A cis fatty is natural product. However, some people want to make saturated fatty acid from the unsaturated fatty acid. Mainly purpose is to make a grain from plant-based oil. And how to do this? They use some enzyme to let's see here. They use enzyme and make this one become a saturated fatty acid. However, this enzyme has a byproduct. The byproduct of this enzyme is that sometimes they're also causing the loss of fatty acid here. And when the fatty acid, the loss of hydrogen here, but when the hydrogen is lost, there's something wrong, something it does not lost in the same direction. Sometimes this two hydrogen is displayed on the opposite side of the fatty acid, and this we call it a trans fatty acid. A trans fatty acid has a different structure of regular cis fatty acid. It's extremely hard for the human body to digest it. So there's a clear evidence that trans fatty acid increase the risk of cardiovascular diseases. So I think in New York City, the use of trans fatty acid is banned. So, and then this fatty acid, and then, so what is a triglyceride? Triglyceride is a glycerol. Glycerol has 3 carbon. Each carbon carry a hydroxy groups, and this hydroxy group can react with the carboxylic group of the fatty acid, so it carry one, another. So this is triglyceride. Triglyceride. Each triglyceride molecule has one glycerol head carrying 3 fatty acid tails. And after this, a triglyceride is completely hydrophobic here. And triglycerides is mainly a storage molecule in our body, mainly stored in the adipocytes, which are fat cells. And in humans, we can convert the dietary carbohydrates into fatty acid, into triglycerides, or of course we can store dietary fat as a triglycerides. But once the carbohydrate is converted into triglyceride in the body, there's no turning back. All the oil, all the fat we store in our adipocytes stay as triglycerides until we use them. So this is the triglycerides. And what is the phospholipids? A phospholipid is a phosphate connect to another. I think that's very highly polar group, and then to fatty acid. So a phosphate has this polar or hydrophobic. A phospholipid, hydrophilic, has one hydrophilic head and 2 hydrophobic tails. And this, I wish you can remember something we talked about in last class. This is a typical surfactant, which means it's one side it has hydrophilic head and the other side has hydrophobic tails. And then what's the function of phospholipids? It's extremely important for the cells because they made up the cell membrane. All the membrane, the inner body, is made of this. We call it bilayer. Oh, not this. Bilayer. The bilayer means the phospholipids, actually, they can do this spontaneously with the head pointing outwards, with the tail pointing inward. And this inward, this is hydrophobic. In this hydrophobic area, some other molecule can exist here. What kind of molecule exists here? That's a thing we talk about later. Something. I don't know how to call it. You also have cholesterol. Cholesterol is also a type of steroid. And whenever we talk about cholesterol, it seems bad because one thing is definitely true. High blood cholesterol increase the risk of cardiovascular disease, which is definitely true, very, very solid. However, please keep in mind, high cholesterol is very important for our body's function. In the memory, so phospholipid is the primary structure component of the memory. However, it's not the only component. In the memory, about at least 30% of the memory is contributed by this thing cholesterol structure. I'm not sure I can draw this. It's not required. It's basically 4 circles of carbons. It all exists here, and the cholesterol is important to provide the fluidity, means make the membrane flexible. It can make different shapes, and then provide integrity. I'm not even sure my spelling is correct. Integrity means it's not easy to peel off a memory. It always sealed very well. I mean, probably kind of sealant or silicone if you ever like help seal your window, something like that, cholesterol. But not exactly the same, but similar. So basically, cholesterol is very important to our body. It has many different functions, and also cholesterol is the progenitor, which means from cholesterol we can make other molecules. For example, sex hormones like testosterone. I'm not sure. Estrogen, sex hormones, estrogen, and vitamin D. And other hormones like cortisol, glucocortisol is also a steroid. So basically, they are very important to our health. We cannot live without them. However, sometimes they do, causing problem. Again, as I mentioned, high blood cholesterol directly related higher risk of cardiovascular disease. However, as I mentioned, it's still controversial whether the diet cholesterol really directly control the elevated blood cholesterol, because cholesterol level in the blood is highly regulated. So far, I don't think we have a clear conclusion of how cholesterol, let's say, is elevated in the blood. So at the last slides of this topic, we briefly mentioned the vitamin and the minerals. And I won't write anything, just briefly say vitamin A contributed I. It makes say essential components of the molecule, the proteins that sensing the light. The vitamin A. Vitamin B is a big family. And all of those are water soluble, and most of those involved in the glucose metabolism, which will be the next topic. And then vitamin C has multiple functions. I say antioxidation, and also is important for the tissue repair things. And then vitamin D is particularly important for the absorption of calcium. And then several of the minerals. Let me think about iron. Iron is the essential for the blood cells carry oxygen. And iodine is essential for us to produce the thyroid hormone. And what else I mentioned here? And the sodium potassium is multiple functions, which have about more in the future. And I think that's magnesium. Magnesium also has multiple function, not that important, but not that not everything is important, but not that critical as a calcium and sodium potassium. However, they are one of the most easy deficiency mineral in the US, because you can mainly get magnesium from the green leaves. And lastly, calcium. Calcium is the most abundant, but most of those does not exist in the form of ions. They mostly exist in the teeth, the bones, give the strength, and the compounds that are made by the calcium and the phosphorus, call it hydroxyapatite. They are the strength of our body. And then there are some calcium existing in the ions in the body. It's not a very high concentration, much lower than sodium or probably even than potassium, but they are very, very important, because calcium is the trigger of, like, say, muscle contraction, neuron fire up, and, like, say, gland, say, hormone secretion. So it's extremely important. So that's it for this topic. And please remember to do the quiz by the end of the Friday. Okay. Good luck.